Okay, so let's start. Welcome everyone, and it's a pleasure to me to have introduced you, Kevin Dorney, here in Salamanca, to have visitors after the pandemic. And well, let me just briefly introduce you, Kevin Dorney. So Kevin Dorney is a Marie Curie postdoc at ImecWorld-Leading in Belgium. ImecWorld is it's not it's kind of different of what we are used here because it's an RI center, research and innovation center. And well, Kevin moved there like 1 year ago, more or less, from Colorado. He did his PhD studies in Colorado, University of Colorado. We can say that Kevin is a multidisciplinary scientist because he started biology. He moved to chemistry. He did chemistry, and then he moved into physics. So
running away from the squishy things.
And he did his PhD in the group of Henrik Captain and Margaret Murnell at the University of Colorado in Boulder, where we have a great collaboration with our group. So he was the guy doing most of the experiments that we were able to propose here, all these things of the self-torque we did and the things with vortices. So this was the guy, he was the real expert that did all those things, and we are really, really happy to have you here. So I will start speaking because you are the important person.
Yeah.
Kevin, please.
Excellent. Thanks, Carlos. And thanks, everyone, for coming this morning. It's a real pleasure to actually come and visit Salamanca, especially after the close connection we had during my PhD. And I've really enjoyed visiting the city for the past yesterday and seeing how beautiful it is. And so just really happy to be here. And thanks, everyone, for joining. And yeah, we'll jump right into it. So yeah, as Carlos mentioned, my name's Kevin. I'm a postdoc at ImecWorld within ImecWorld's AttoLab, which is a recently constructed EUV laboratory based on high harmonic sources, and then deploying these high harmonic sources for metrology, spectroscopy, or even lithography to help benefit the research of the semiconductor industry. So just a quick outline. I'll give an introduction to who I am and why I'm here and why I know Carlos and a lot of the group here. I'll introduce ImecWorld and its research activities, and then also motivate the need for ultrafast spectroscopy, microscopy, and lithography from a semiconductor standpoint, why they would want to build a lab like this to help benefit their research methods. And then finally, we'll get to the thick of the presentation today, and that's going to be all about the AttoLab at ImecWorld. So I'll go over the infrastructure, our main experimental end stations. There won't be a whole lot of data in this talk. This is one of the things of working with private companies and stuff like that, but I'll give you an idea of capabilities and what their interests are and what we as an attosecond science community can really bring to this industry. So to start, as Carlos said, I started in biology actually in a small town in Ohio in the US where it's very flat, it's very green, there's lots of farms, not many people. The cows sort of outnumber the people there, I don't know, 20 to 1, something like that. But I eventually left these green pastures and farms and moved to Boulder in Colorado. And so here's a picture of Boulder. It's nestled right up against the mountains. I mean, you go 20 minutes drive in and you're at 2,000 meters, something like that. So it's a really beautiful place to be able to live and do research. And there's a smallish campus here, and that's CU Boulder, and that's also where GILA is. So GILA is a physics research institute that's joint with the National Institute of Standards in Boulder, and that's where all of my PhD research was done. So it was really nice to be able to do that because, as you know, Colorado is very scenic. It has all these nice mountains and things like that. And aside from the nature, we were able to do a lot of exciting science there. So I did my PhD in the Captain Murnane group, as Carlos mentioned. And it's a group with sort of a wide experience in ultrafast light science, spectroscopy, nanoscale imaging. And so there's a lot of research areas within this group, sort of deploying high harmonic ultrafast sources for various spectromicroscopies. And a large part of my research in the group, along with people here in Salamanca, was to really work on how we can develop new paradigms in attosecond nonlinear optics. So how can we play and control the emitted HHG light or the emitted EUV light in high harmonic generation? We had a lot of fun really twisting, bending, shaping light sort of almost at will in these experiments. And so that brings me to the not the French connection, but the Salamanca connection. And so the connection here is we've always had a strong connection and collaboration with the group here. And we did a lot of fun stuff. For instance, looking at high energy soft X-ray harmonics. This was before my time in the group and really sort of the beginning of looking at sort of mid-IR drivers to really push the photon energy of HHG sources. And then also, as I said, messing with the circular polarization, so generating circularly polarized harmonics and a whole variety of geometries and also interactions and using these circular sources for some spectroscopies in the soft X-ray regime. And then lately, as many of you know, we did a lot of work, a lot of exciting work with OAM and structured HHG, really doing fun things of creating self-torque of light and actually demonstrating that experimentally, and then also using OAM-constrained conservation rules or spin-constrained conservation rules to really generate unique shapes of OAM beams with different circular polarization. This was a lot of fun, but I'm going to talk about none of this today. I think many of you are quite familiar with this, and of course, if you have questions, I love talking about this. I could talk for days about this. But really what I want to do is talk about my research at EMEC and what we've been up to for the last sort of year and a half here. So I traded the mountains for, again, a very flat area. This is a picture of EMEC. It's located in Leuven, Belgium, which is just about a 20-30 minute drive east of Brussels. Leuven's claim to fame before, well, EMEC, I didn't know what EMEC was before I got there, but I did know that Stella is made there. So if you like Stella, well, that's brewed in Leuven, and that's the headquarters of them. But what EMEC is it's a research and innovation technology center for the semiconductor industry. So they have incredible facilities for performing this research. Here you can see a picture of a what's called a 300 millimeter clean room. It's not 300 millimeters big. That's how big the devices they make are. And the semiconductor industry, what's very unique about this place is there's sort of a handshake relationship between EMEC and industrial partners of the semiconductor industry. And so what we do at EMEC is partners will station employees here and allow them to work in the research facilities hand in hand with EMEC scientists. And it creates this nice cyclic flow of information, know-how, expertise, technologies that can directly benefit the practicalities of the semiconductor industry. So when they have problems they want to research, they often come to EMEC to do that research, and that feeds directly into the products that they produce. And for instance, a lot of the products like the chips in your smartphone, stuff like that, comes from research at EMEC. So EMEC's really just here to benefit the semiconductor industry and the research they do. Now, EMEC has its hands in a lot of different sort of pies, I guess, for the semiconductor industry. These is just a few examples of some of the things that it actually does research in. So there's all kinds of research activities from life sciences to chips, photonics, even computing and AI is starting to get a pretty big growth spurt at EMEC. And in regards to AttoLab, two of the main things that they really work on at EMEC is advances in lithography. And lithography is actually how the chips in your smartphone are produced. It's a way of writing small patterns onto a device, and then through subsequent chemical physical processes, you can develop these patterns, and these eventually build up the small components in your chips. And I'll go over that a bit more in detail here in a second. These are done. This lithography is done with these giant machines here. These are called lithography scanners. They're the ones that actually perform the optical writing process, and EMEC has a few of these, so they get to do a lot of research on this. But this is what's at a lot of your chip making companies, Intel, Samsung, people like that. At the same time, though, they're also pushing advances in device architecture and composition. Chips are becoming more complicated. So there's more materials that are actually going into your computer chips now, your sensors, than have ever been previously done. For instance, there's interest in quantum computing using 2D materials and sort of the spin properties of these materials using vallectronics. There's also interest in 2D materials to replace typical silicon transistors. And also, if you have a hard drive or any kind of memory stick or something like that, you have a highly structured nanomaterial that operates on principles of magnetism to store your data. So we're constantly exploring new materials, and it's these two thrusts that are going to really push for the semiconductor industry to want to use EUV light in order to study both of these processes, the materials and the lithography side. So just a brief introduction to lithography. So the chip in your smartphone is actually something quite complicated. It's sort of like a giant sandwich with many layers of many different materials. I mean, it can be up to 1,000 layers in a small chip that's only a few millimeters tall. And the way that these individual chips are made is each individual layer is subjected to this lithography process. So these small components are on the order of nanometers. We use light to write small nanometer features in some photosensitive material. We then develop it away. Sometimes we implement some metal ions in it, you know, if we want to create sort of conducting wires or something like that. And eventually this process is then repeated. And the main unit here is something called a photoresist. And that's just a light-sensitive organic polymer that has some sort of chemical physical change when light hits it. And so what they try to do here is at a fundamental level, when we expose these photoresists, it's all about creating nano patterns in them. So here, these could be, for instance, conducting wires that are connecting different parts of the chip. Here, these are holes or pillars. These are used for usually magnetic materials or memory materials and storage. But the goal is to write small patterns. And the smaller the patterns, the better our chips are. The more transistors, the more components we can fit on a chip. And then the more efficient, the faster our devices become. And it turns out the smallest dimension, as you could probably guess, is related to the wavelength of the light that's actually being shined in there. And that's why the semiconductor industry has, over the past 2 years, they're starting to use EUV light at 13.5 nanometers specifically in order to do this lithographic process, because it gives higher resolution in these printed lines. Now, this is a complex process, how it actually works. So if we look at sort of the first step, what happens is we take a photoresist, we put it on some sort of substrate, we expose, and that causes a solubility change, actually, or some change that we can then use processing to remove the exposed areas. And eventually what happens is how we create those shapes is in a process called development, usually done with chemicals. It just washes away the area where the light exposed it. Now, the issue with this is we'd like to study this process and optimize it. EUV technology for semiconductor industry is maybe 10 years old, something like that. But the issue with doing research is if you want to do research on this, typically you have to buy one of these machines. This is an EUV machine from a company called ASML. They split off from Philips in the 80s. And these things cost about 200 million euro to work. So yeah, you could write, I don't know, 100 ERCs maybe, and then you could get one of these, or you have to be a semiconductor, big company in semiconductors. And so the issue with that is why we want to study this is this process is highly complex and very complicated, as you might be able to imagine. We're using EUV light, which is ionizing radiation. And so what happens during this process is we sort of know what's happening, but we don't know the details. We just know the general steps. When light hits a photoresist, it typically generates primary photoelectrons, and that's on the time scale of absorption events. So these are attoseconds that these electrons are generated and released. The electrons themselves undergo scattering processes. That can be a few femtoseconds, 10 femtoseconds. The electrons then do chemistry to the material because it's the electrons causing the chemical changes here. And then also there can be molecular diffusion, bond breaking. This can be on picosecond timescales. And so the issue with all of this, as you can see, is it involves a variety of species, electrons, molecules, the photoresist itself, which is an organic polymer, hard to model. And all of these happen on fast timescales, very fast timescales, which cannot be accessed with a $200 million machine like this. So what this did is this created a demand for accessible, ultra-fast, and bright EUV sources that you can do research on. And that turns out that high harmonic generation provides a platform for this. Now, at the same time, I talked about chips getting more complicated. And in this regard, the materials that we're using in chips are exponentially increasing. And as they're exponentially increasing, the dimensions of these components are also shrinking. So now on top of ultra-fast EUV sources, we need elemental characterization, specification, and we need something that can resolve small structures. Again, we're hinting at short wavelength EUV light. And of course, it wouldn't be a ultra-fast talk if I didn't put one of these plots of time versus length scales and tried to motivate why we want to study some of these things. And from a semiconductor standpoint, there's a lot of benefits to having ultra-fast coherent EUV light because it can also be, not only does it give that elemental, chemical, and spin specificity, but it can be used to non-destructively image structures as well. And a lot of these new materials that the semiconductor industry is bringing in for magnetic memories, valiant spintronics are quite complicated. They're topological in nature. And so because of this fast and highly structured future, we need things that can actually resolve these processes and on these length scales of nanometers to sub-nanometer. So, okay, so that brought some people together at EMEC and wanted to figure out how could we solve this issue? How could they build something that would give the research capability needed to answer these questions? And the idea was to sort of take a marriage of two aspects from academia and industry. And as we know in academia, when we work in the labs, we develop these incredible measurement capabilities, these very novel techniques that can really get at things that we never thought we could observe before. And we're quite good at these ultra-fast nanoscale spectroscopy, microscopies on a variety of systems. Now, for the semiconductor industry, they're more engineering in this sense. They can manufacture these devices. They can make these very unique materials that we're often looking for the right application for, and they can engineer them to be built however we want, whatever thickness we want, whatever composition. But despite this, there's still a gap to when we do research on these novel materials in the lab to when the industry actually picks them up. And so this technology gap, we wanted to bridge this by developing a lab that can take samples, know-how directly from industry, and then use the advanced techniques that we've been developing in university labs for the last 3 decades to answer these questions. And so this is a joint lab between EMEC and 2 other small companies. KM Labs is a laser company. They're in Boulder. I did my PhD in the group, but this is the company. And then Specs is a photo emission company that specializes in photo emission tools located in Berlin. So this is what the AttoLab looks like at EMEC. It's designed as sort of a user-oriented, accessible, ultra-fast EUV laboratory employing high harmonic sources for spectroscopies and microscopies. You can see from these pictures that it is quite a crowded laboratory. We have 1 optical table, 1 laser, 2 EUV sources, and as you'll see, about 4 experimental end stations. So it's quite a busy laboratory, but it gives a lot of variety and a lot of capability for what we can do. And so the idea here is to develop spatial temporal microscopies, spectroscopies that will aid the semiconductor industry in their research. And in this thrust, we have 4 main approaches for AttoLab that we're foreseeing at the moment. And this is interference lithography to help us study the lithographic process, time-resolved spectroscopy, coherent diffractive imaging, and photo emission spectroscopy. And so with lithography, what we'd like to do is we'd like to provide a test bed for those giant $200 million machines where they can start screening materials. They can bring their materials, do the lithographic process, and actually test, does this resist work? Does this material work? Does this improve those nanoscale lines that I'm making? Does that help improve my chip performance? At the same time, and something I'm intimately involved in with my research is time-resolved spectroscopy. So really looking at molecular dynamics, mechanisms of EUV energy transfer after the light hits the photoresist. So this is sort of an inverse to the typical pump probe experiments with EUV light that we do. Typically, it's a visible IR pump and an EUV probe. Here, we're doing EUV pump and then probing with other wavelengths to really get at these ultra-fast chemical dynamics. So to look at, generations of radicals, things like that, that might influence the chemistries that happen in these photoresists. We also are deploying coherent diffractive imaging. With these nanoscale devices they're making, the inspection methods are actually quite difficult for the industry. They're often very destructive or they're not chemically specific. And so CDI provides a nice method of being able to image devices, using X-ray vision, being able to look through transparent materials, And then also coupling this with sort of in a pump probe scheme to do something called stroboscopic imaging or time-resolved imaging. And then finally, we have a photo emission spectromicroscopy beamline, and this is really used for characterizing new materials. So 2D materials, some of these topological insulators that are making their way into these quantum computing devices, and also being able to look at electron dynamics upon exposure, because the electrons, as I mentioned, drive this mechanism in photoresists, and so being able to look at that would really give some great insights. So this is a cartoon rendering of the lab, kind of gives a bird's eye view. As you can see, we have a Ti-Sapphire amplifier. It runs at about 15 watts at 5 kilohertz. This gives us a few millijoules of pulse energy to play with. And it is a multi-pass amplifier, so it gives us a nice short pulse duration for driving the harmonics. We have 2 EUV sources. These are from KM Labs, and I'll go into the details of how those work and how they produce their light. And then we also have an OPA that's tunable from the near infrared to the mid infrared for our spectroscopy. Now, the experimental end stations, here you can see a giant chamber. This is for performing lithography on what's called 300 millimeter wafers. This is what they make your devices on. They're these big silicon discs that they actually do the lithography on. We also have a small CDI end station for just looking at either device materials or something called EUV mask. That's what helps put the pattern on these during the lithography step. We have a time-resolved spectroscopy beamline that's mostly dedicated to studying photoresist, but also other thin films and materials. And then finally, we have a, there we go. Whoops, too far. We have an ARPES angle-resolved photo emission spectroscopy and a electron microscopy tool that's used for our photo emission spectroscopies. And that's also coupled with a pump beamline for time-resolved studies. So I don't think I have to spend a whole lot of time telling everyone what high harmonic generation is here, but what we do in this lab is we do our high harmonic generation inside a hollow capillary. So we pressurize a capillary with high pressure gas, and then we send in an intense femtosecond laser pulse into this gas-filled capillary. And by the process of high harmonic generation, we generate our coherent laser-like EUV light for us, not really X-ray light at this moment in AttoLab. And so if you could put on your quantum binoculars and see what this process actually looks like inside the capillary, we have our atoms. They have an electron wave packet that's sitting in its ground state. The strong laser field comes, and that's going to distort the Coulomb potential of this atom and can lead to tunneling ionization of the electron wave packet. Once it's freed from its atomic prison, this electron wave packet can then propagate in the field, gaining energy. And if it's lucky enough, it will find its way back in close proximity to the parent ion it's ionized from. And when it recombines, it has a small chance to recombine. It can emit a photon that conserves the energy of that process, which is related to the ionization potential and the ponderomotive potential, the energy gained in the laser field. For us, we use long pulses, 25 femtoseconds, so we don't produce single attosecond pulses. So for us, the process looks something like this. When our laser field comes in, it repeats this 3-step process that we just saw here and leads to a burst of radiation every half cycle of the laser field. As these bursts add coherently, if you put your Fourier hat on, you can imagine that periodic time bursts give you a periodic structure in the spectral domain. So we do not generate one specific wavelength of light. We generate a whole spectrum, and then we use mirrors to sort of filter the spectrum back down. Okay, so here's really the heart of the AttoLab. These are the EUV sources that we have. And as I said, they work on performing HHG in a capillary. So here's a picture of what the cell actually looks like. We guide the laser light through it. It ionizes. You can see the plasma, and it emits the EUV light on the other side. We do this in 2 different gases, or well, 3 different gases: argon, neon, helium, and this gives us quite a broad tunability range for the EUV light, something on the order of 26 to 130 EV. Right now, we're set up for linear polarization, but we also have plans to do elliptical and circular, not just because it's fun, but because there's a lot of interesting dynamics, especially with spintronic materials to study. And we get quite nice beams out of this system. They're highly stable, they're focusable to small dimensions, And the way the system is set up, we produce a spectrum that actually almost peaks exactly at 13.5 nanometer, which is something a bit rare in HHG setups. It's often very difficult to get a spectrum that peaks right here. But with the engineering of this setup, this is a routine spectrum we get almost on a daily basis. And so, yeah, with these systems, not only do we get nice spectra, we also have very nice stability out of them from this laser system. Here you can see this is generating harmonics at around 30 nanometers, and we have really quite high flux from these systems and very nice long-term stability in the lab. Also at 13 nanometer, we can deliver almost 10 to, well, this is when the system was new, so that's a little higher than now, but we could deliver 10 to the 10, 10 to the 9 photons per second on target, which gives us a lot of flexibility in these spectroscopies. And this gives us a lot of room to play around with doses for these photoresist studies, and really gives us a nice robust system for these spectroscopies. Okay, so getting into the beamlines here, the first one I'd like to start with is our time resolved spectroscopy beamline. This is mostly for studying photoresists. So going back to this EUV lithography, the reason we want to study photoresists is there are issues with the sort of stochastic nature, random nature of electrons being generated by EUV light that yields failures in devices. And so when they do the lithography printing, sometimes those little lines are not always straight. They have little breaks in them, they're connected. And there's two primary reasons why this happens. One is just a shot noise argument. The EUV light is a much shorter wavelength than what was typically used for lithography, so there's less photon density. So shot noise becomes a problem. One of the real reasons we think that is causing this, though, is really the complex chemistry. And here's just a small cartoon of what happens when we send EUV light into one of these organic photoresists. It can generate a primary electron, and this electron can go on to cause all sorts of chemistries that is different than the desired chemistry. So the idea is that for a potential path forward, let's leverage the radiochemistry, and then we can engineer these photoresists to respond more appropriately to EUV light, giving us better performance for lithography. And so what the idea here is if we take what looks like a typical photoresist, so it's a polymer material, a blend of different polymers, and it has these additional chemical agents added to it called a photoacid and a quencher to help initiate the reaction. So when we shine the EUV light in, what we would really like to do is we want to photoexcite an acid that's going to remove a part of one of the polymer chains. And that's going to cause a solubility switch. That's going to change its solubility in a solvent. But what really happens is something crazy like this. The EUV light hits, electrons go all over the place. They can excite molecules that are in the polymer backbone. They can create free radicals in the polymer backbone. And that creates a whole series of complicated reactions that really, in the end, is something quite simple. We just want to remove some kind of chemical group here so we can change the solubility. So what we're going to do to study that complex reaction is employ EUV pump mid-IR probe spectroscopy. And so what this looks like is we have our EUV beam coming in, hitting our sample, and a mid-IR probe beam. And so before the EUV light hits, we might observe a static absorption spectrum, some kind of characteristic peak of a molecule or vibrational mode. And as we change the time delay, though, eventually we might see, when the EUV comes just first, we might see the appearance of new peaks. And as we further scan this time delay, we'll see the appearance of new peaks, the disappearance of our original peaks. And the idea is to, using theory, to calibrate our spectrum and be able to correlate changes in the IR spectrum to the production of chemical intermediates, to be able to see what are the chemical changes actually happening in the photoresist. And so that's all nice as a cartoon, but in the lab, what it really looks like is something like this. We have an EUV beamline with a bunch of routing mirrors that come in, a monochromator that employs molybdenum silicon mirrors to turn this into 13.5 nanometer light. And then we have a mid-IR delay line that we use for probing the dynamics. And so to generate this mid-IR light, I mentioned we have an OPA. This OPA is quite tunable, quite stable. It produces nice broad spectra this is in wave numbers, but this is probably a 3 micron to about 12 microns, somewhere in there, and allows us to cover a lot of the vibrational modes that are characteristic to photoresist materials. And at the same time, we have a sample chamber for this, which is quite straightforward. It holds small pieces of those big wafers I talked about earlier with photoresist on them. We excite with 13.5 nanometer light. And then we have 2 beam lines, well, 2 ways that we can do the spectroscopy. One is through transmission measurements here to go through the bulk, because silicon is transparent to VIR. And then we can also do reflection if we wanted to, if we suspect for any reason there's a surface effect in these resists. And so what this gives us is a nice beam line with tunable mid-IR pulses with a decent time resolution, which sort of varies depending on the pulse that we're producing, along with a stable delay line and a flexible chamber for performing these experiments. The next thing I want to talk about then is going into the interference lithography studies in AttoLab. And we have 2 ways of doing this. One is in a big chamber, and then we have a smaller chamber for smaller samples. And so for these 2 methods that we deploy, one is referred to as a Lloyd's mirror device. This is actually a very, very simple device. It takes a reflector and it pushes up against a photoresist, and then using a partial reflection of the EUV beam, it creates an interference pattern on the photoresist. So what this looks like is we have our reflector here. We use ruthenium because of its good reflectivity at 13.5 nanometers. We put that at a right angle with the photoresist material, and by adjusting the relative angle of this holder, here you can see a rotation stage with the EUV light, we can get a partial reflection that then interferes with the main beam on the photoresist here. And what that does is that creates a linear grating. So it's quite simple interference phenomenon with a pitch that's equal to, or a pitch or a wavelength of this grating that's equal to the wavelength of the light divided by the sine of this angle. So from this, we can actually print very small features, something like 20, 30 nanometers with a relatively simple device. And we like this one because it's a good test device. It has small samples. It's very quick. And allows us to diagnose things, see if we have the flux, the stability in our beam to be able to actually even do this. Another way we plan to do this is a large chamber that can do it on a full 300 millimeter wafer for interference lithography. So this is the big chamber. It has some beam routing optics, and then it does the lithography down here on the bottom. And this one's a bit more complicated of a way that we're doing this. We're actually going to split the beam first using a coated prism, and then recombine the beams back on top of each other on the photoresist. And the reason for doing this is this is flexible. It can change its pitch range over a much larger range than this simple device can. And because we're not using partial reflections, we're using the whole beam intensity, it actually prints a lot faster. I won't talk too much about this device, this chamber, because it's still being built out. But for that Lloyd's mirror device, we actually were quite successful already in printing lithographic patterns with 13 nanometer light. So here it might be a little bit difficult to see, but you can see those sort of linear gratings patterns on an exposed coupon sample. This one is with a metal oxide resist that's a little different than the ones that I had mentioned previously. But if we take, sort of an integrated line out of here, we see that we actually formed a pitch or a wavelength of this grating that's on the order of 20 nanometers. Now that number might not sound so much, but it's actually a world record for this sort of tabletop system, and is a value that they can't actually do in those EUV scanners. So we were quite excited about this because this showed that EUV light, especially from high harmonic generation, has the capability to actually do lithography. We can use this to study the lithographic process. And so if you'd like to read more, there is a small press release about it. IMEC was quite excited about us to be able to do this. And we were too, because if that didn't work, basically half the lab would have to be shut down. So that was a really nice result for us. We were able to breathe a sigh of relief. Okay, so moving on now to the CDI chamber. CDI, this one is still being built out, so I don't have too many pretty pictures to show you, but the general idea with this one is in CDI, where you shine EUV light on a sample, you collect a diffraction pattern, and you form an image from those diffraction patterns. It's just a phase retrieval phenomenon. you can do non-destructive imaging with a resolution that's actually proportional to, in lateral space, to the wavelength of the light that you're using. And axially, it's proportional to a fraction of the phase of that light, which can give you sub-nanometer accuracy in the EUV range. And so our goals here are to develop two different kinds of CDI. One is imaging reflectometry. So this is where you collect diffraction patterns from a sample of interest over a variety of angles. And then you exploit either the phase shift or the changes in amplitude for different materials as a function of increasing incidence angle. And so in some regions, if you have a certain sample, you can actually get well-separated values for the phase or for the amplitude of different materials. And this allows you to do chemical imaging. And this is quite important for the semiconductor industry because of, again, I mentioned the complexity of these chips, the materials on top of each other. They'd really like to be able to image specific ones at a time without destroying the sample. On another thrust, there's also a need to look under layers or do what we call buried layer imaging for the semiconductor industry. So as they build these chips up, sometimes they put a layer on top of one another. Well, they really don't know when one layer goes on another, how that affects the layer below. We all know there should be diffusion of materials between these things, and so it's really unclear how that affects the performance of the device. And this just highlights some work, well, both of these are from my previous group, but you can actually exploit the relative transparency of EUV light to do buried layer imaging. And so here this is showing images of a sample that was coated with a small layer of aluminum. And we would like to use this to be able to image interfaces to really get an idea of what sort of chemical or solid state diffusion is happening in these devices, and then how does that affect performance. And then finally, I'll get to our photo emission tools. So this is using angle resolved photo emission, electron microscopy, and then there's some other characterization methods in there. And then for this, we also plan to use the same mid-IR OPA as a pump pulse. And then also we have an IR and UV pump line over here that we can do a second harmonic, third harmonic of the TISAP amplifier for time resolve studies. And so this is what the tool looks like. It's from Specs, as I mentioned, which is a company in Berlin. And it's actually quite a compact ARPA's tool coupled with a PEEM. And so this gives us a lot of different capabilities with this single individual instrument. One of the main capabilities, as I said, is ARPA's, that's angle resolved photo emission. And here we actually already have this, this tool up and running. This is a band structure which was measured on our tool of bismuth selenide. This is a topological insulator that's of interest for quantum computing or spintronics applications. And they actually make this at ImecWorld. So they make it, they can give it to us. We can test different formulations and see how that affects the band structure, which ultimately affects, you know, how you can populate or depopulate these values using that for spintronics or quantum computing applications. On the other side, we also have a PEEM, which we're currently working on getting up and running right now. And so in PEEM, instead of getting the energy spectrum of the photoelectrons like you do in ARPES, or sorry, getting the 2D spectrum like you do in ARPES, in PEEM, you get a 1D or just the electron energy from the photoelectrons. And so we would like to use this to look at, for instance, and in particular my research, the generation of electrons when we when we shine EUV light on an EUV photoresist. So we know that it does produce a spectrum of primary and secondary electrons, but we really don't know much about the timescales of these electrons. We really don't know much about when they're produced, what they do, and so combining this with a streaking measurement will give us insights onto sort of the timescales that these electrons are emitted and how they're influencing the ultimate chemistry in the resist. So with that, like I said, it's a talk that can't show a whole lot of data, but it can show capabilities. So with that, I would like to summarize, you know, the capabilities that we have in AttoLab and what how these capabilities came from what the semiconductor industry needs. So what they need is bright, accessible EUV sources, and high harmonic generation provides a nice platform for that. They need ultra-fast spectroscopies to study these complex mechanisms in photoresist. So that comes into sort of our pump probe techniques that we've been developing across the world for the past few decades. Interference lithography to give them a test bed for new photoresist. So again, to the bright nature of these EUV sources that we need. Also, we have nanoscale coherent diffractive imaging that we're bringing up for non-destructive interrogation of these materials. And then finally, this semiconductor industry is really starting to understand the importance of band structure and also electron dynamics in not only the materials, but also the devices that these materials are going to go in. So really all of these thrusts were sort of born out of conversations with the semiconductor industry. What can we do to help? What can HHG do to help? What can ultrafast EUV science do to help with these research directions? And so we're a growing team now in AttoLab. We started out, it was just 3 of us at the very beginning last year, but we've since been able to grow our team quite well. So a lot of this work was put together by 2 principal scientific members at ImecWorld that helped to hire a slew of postdocs and also some staff scientists to help with to help with implementing some of these techniques. And then in addition, we also have just recently partnered with an ab initio group at ImecWorld to really start modeling some of these chemical processes. So even from a theoretical standpoint, there is a need to perform simulations and things like this to help us understand these complicated processes for this industry. And then now we finally got a bunch of PhD students through the university and in Leuven that will help with a variety of these techniques. And so with that, I'd like to thank everyone for the attention, the opportunity to come speak here. And of course, if you have questions, please fire away. I love talking about these subjects. So yeah, thanks for your attention and happy to answer any questions that you might have.